In the last unit, we took a look at matrices and some of their properties, like how to multiply them, and also we looked at different scenarios for what you can expect out of solutions to systems of differential equations. Let's put these things together so that they can help each other out so that we can find solutions to systems. So we'll look at the link between linear systems and matrices, and we will start learning how to go back and forth to see how information from one can help inform about the other. So the first thing we need to look at is when you have a system of linear equations, how you can immediately put it in matrix format. And here's a simple 2x2 example, 2 equations and 2 unknowns. So the equations are there at the top. If you remember how matrix multiplication works, you should be able to recognize that these two sets of math expressions, the equations on the top and the matrix product on the bottom, represent exactly the same thing. Right? If you look at the matrices on the bottom and you carry out the multiplication on the left, remember that you're going to do essentially a dot product of the top row of the left-hand matrix with the column vector xy. So you would get 2x minus 4y. That produces something that wants to be in the top spot, and since that's equal to the thing on the right, that has to be equal to 7, and there's your equation, 2x minus 4y equals 7. Similarly, for the second row in the matrix product, you would have 1x plus 2y, which has to become equal to 3. That's the second equation. And fortunately, visually, this is really simple. If you look at the equations on the top, just strip off the coefficients, load them up into their own matrix, make a little column vector with the variables, and then the right-hand side goes into its own column vector. And remember, when we say column vector, we're still talking about a matrix. It's just a matrix with one column. Here's a bigger example, 3 equations and 3 unknowns. Having seen what we just did on the last slide, take a second and see if you can imagine what the matrix version of this system of equations is going to look like. And there it is. The coefficients from the left-hand side populate their own matrix. That's called a coefficient matrix. The variables go into what's called the solution vector, x, y, z, and the right-hand side goes into its own column vector as well. So what we've seen so far in our talk about solutions and just looking at this is that the really good information in a system of equations is all buried in the coefficients. The variables themselves don't really matter, whether they're named x, y, z, or a, b, c, or x1, x2, x3, it doesn't matter. None of that stuff matters to the solution process. So let's get the variables out of our face. And we're going to build something to help us called the augmented coefficient matrix. And all that means is we're going to take, let me back up a page. So in this 3x3 system, right, that vector x, y, z is really irrelevant to the problem solving process because all that does is list us the names of the variables. It's the coefficient matrix and the right side vector that have all the good stuff. And we don't need to carry them around as two separate things. We can put them together into one larger matrix called an augmented coefficient matrix, where we just take the right-hand side and put it in the same box as the left-hand coefficients. And when we see that, we just have to remember that in this context, that right-hand column with the 7 and the 3, that goes with the right-hand side of a system of equations. So kind of remember there's a little equal sign there in between the left-hand coefficients and that very most right-hand column. And so the augmented coefficient matrix for the 3x system left at the bottom of the screen there is again the coefficient matrix from the left with the single right-hand side vector also stuck in the box. Sometimes in books you'll see a vertical line put in there to separate the coefficients to the left and the right-hand side vector, but frankly in this typesetting it's kind of awkward to do that, so I'm not going to. We just have to remember that right-hand column is the right-hand side of the equations. So having seen that, can you go backwards? If I show you an augmented coefficient matrix, can you reproduce the system of equations it goes with? You have to pick your own variable name, so we'll just stick with x, y, z. Let's not stress ourselves. Remember that the right-hand column is the right-hand side of the system of equations, and the rest of the numbers become the coefficients to the equations. So this augmented coefficient matrix represents a system of 3 equations in 3 unknowns that looks like this. Now when you see that system and you look at it, right, if we wanted the solution to that system, we'd be looking for the values of x and y and z that satisfy all 3 equations simultaneously. Is it obvious what that solution is? The answer is no way, not yet. So here's a different augmented coefficient matrix. Can you tell the system of equations that it represents? It's that one. Because there's a lot of zeros, so a lot of the variables will drop out when you reproduce the equations. Is it immediately obvious what the solution to this system is? The answer is yes, it's right there in front of our face. The solution to this system is x equals 2, y equals 1, z equals 6. We can read it right out of the augmented coefficient matrix. And so this gives us a clue into what our problem-solving process is going to be, is that if we can get our augmented coefficient matrices to look like this format with lots of zeros, ones down the diagonal, and then numbers on the right-hand side, we can read the solution to our system of equations right out of there. So the struggle is going to be, how do we take an augmented coefficient matrix and make it look like that? That's what's coming up in the next video of this unit. So just for a moment, before we dive deeply into that problem-solving process, let's just practice more with these augmented coefficient matrices. For example, this one. How many equations and how many variables? So in these matrices, remember that each row is going to correspond to an equation, a linear equation, and the right-hand column is the right-hand side of those. So the 1 and the 4 that you see here go on the right-hand side of the equal sign in a system of equations. And so what we're looking at here is 2 equations, but with 3 unknowns. So the 1, and the 0 are the coefficients of unknowns, of variables, and so also the 2, the 1, and the negative 1. So 2 equations, 3 variables. This one, the right-hand column, is the right-hand side of the system of equations. Each row corresponds to an equation. So the 4 and the 2, the 1 and the 2, the 1, the negative 1, and the 0 and the 5, those are all coefficients of variables. There's 4 equations, so that there's 2 variables. Here, 3 rows, so 3 equations, looks to me like 4 variables. The 6, the 4, the 1 would be the right-hand side of the equations. And finally here, 3 equations, 3 variables. Now, the bottom row doesn't really tell us much, but it is an equation. It says 0x plus 0y plus 0z equals 0. That's an equation. It's totally true. It will turn out that in the problem-solving process, not only is it true, but it's totally useless in terms of helping solve for the solution, and that will be one of our visual cues that something weird is going on. So, if you've caught all that about augmented coefficient matrices, you are ready to try a few problems and then move on to Unit 2, Part B.